Okay, in these slides, we want to show the idea of what we're trying to do, the outline. We took before in the previous chapters that if you have some kind of charge distribution, we took several kinds of charge distribution. We took point charges, we took charges on a line or a contour, we took charges that can be distributed on a surface, and also volume charge distribution. Whatever the charge distribution we have, we could describe the effect of these charges in the region around them by something called the electric field. So at every point in space, we could define an electric field vector at that point in space. So it's a field, it exists at every single point in space. Now in this chapter, we want to introduce another way to describe the effect of these charges, but it's now in terms of a scalar field, meaning that at every point in space, you define a number. So there's no vector at every point, just a number. And the number is called the potential. The potential at every point, it's a number. And so we have then this new way of describing the effect of the charges. So we have the new way in terms of the scalar field, the potential. At every point in space, there's a number. And also we have the way we described it before in terms of the electric field, where every point in space we define an electric field vector. And then we need to ask, what's the relationship between these two descriptions? Can I go from one to the other? For instance, if I know the potential, can I get the electric field? If I know the electric field, can I get the potential? And then the most important thing is we want to also discuss is, why do we need to introduce another way to describe the effect of the charges in space? We already have a nice way of getting the effect of the charges in terms of the electric field vector at every point. So why do we need this new method? So that's what we're trying to explain in these slides. So the way we got the electric field before, we had a charge distribution, whatever the charge distribution is, and we were able to use Coulomb's law, kq over r squared. The electric field is kq over r squared, and then you have to get, of course, the direction correctly because the electric field is a vector. So that's what we did before, and if you have many charges, you add the electric field due to each charge and so on. So we were able to get the electric field in a very nice way before already. So now, in the new way of doing things, we're going to do the same thing. Where the end goal is the same. We want the electric field, but we're going to do it in two steps. The first step is, from the charge distribution, find this potential at every point in space, which is just a number at every point in space. The second step, if you know the potential at every point in space, how can you get the electric field? So we're going to cut it up into two steps. Of course, people will say, okay, we did it in one step before, and now you're telling me we're going to do it in two steps, so why make it more complicated? And of course, the idea is that the two steps, in many cases, are easier to do than doing the one step directly. We're going to explain that in detail in this group of files, but I'm just going to give the idea here. When you're getting the electric field due to many charges, you're adding the electric field due to each charge. So you're adding vectors. And adding vectors is not that easy, because you have to add the x components on their own, and the y components on their own, and the z components on their own. But when you get the potential from the charge distribution, you're going to be adding numbers. And adding numbers is very easy. You don't have to worry about any directions at all. And then the second thing, when you get the electric field from the potential, it's going to be very, very easy to do, because you just have to do some differentiation. And differentiation is very easy to do. It's much easier to do than integration. So that's kind of the idea why we want to do this two-step process. And of course, this is just an outline of what we want to do, but we'll describe everything in detail as we go along. So the way we're going to proceed is the following. We're going to first start with this part. We're going to start with the question, if I know the potential everywhere, how can I get the electric field? And then we're going to see how to get the potential from the charge distribution. And then later on, we're going to see what the connection is between the concept of potential that we're just defining in terms of other things that you know about, like the work and energy. So we're going to do that later on. But for now, we just want to focus on these two steps: how to get from a charge distribution, get the potential, and then from the potential, get the electric field.